Yes, yeah, yeah. Thank, thank you, Professor, for the introduction. Thank you. I'm very excited to meet you all. In this lecture series, we will be covering all the fundamentals of wire arc additive manufacturing, how this technology has been developed, and what are the future prospects of this technology, and what are the present research gaps that are there in this technology, which is restricting the industrial adoption. Okay, so all these things we will be covering in this lecture series. Just a second. Yeah. So before stepping further, first let us remember one thing. As of now, we are in the fourth industrial revolution, which is popularly referred as Industrial 4.0. So this particular industrial revolution emphasizes on integrating all the cyber physical system, Internet of Things, and all the digital technologies uh, such as sensors, actuators, and even few other technologies such as big data and even remote sensing. So all these things that are going to be integrated so that less human intervention will be there in future, and we will be getting a highly accurate component with minimal part rejection. So that is what the main motto of the Industrial 4.0. So let us see why. So as we know that what are the manufacturing methods that which we are doing at present, mostly all are like subtractive manufacturing. Let us see in what way the additive manufacturing differ from subtractive manufacturing. So generally the subtractive manufacturing is a top-down approach where a component will be fabricated. Then after that, after once the component was fabricated, the component will be machined to a desired dimension, and a lot of material wastages will be there once it reaches a final geometry. Okay, but whereas additive manufacturing is concerned, additive manufacturing is a bottom-up approach where the material will be fabricated in a layer by layer until achieving a predefined geometry. So here the material wastages are very minimum. Okay, so that is why Industrial 4.0 is pushing the industries to deploy the advanced technology right now. Okay, so let us take an example of conventional casting. In conventional casting, the first step what we will be doing is a pattern preparation. Okay, so it is one of the oldest techniques. Even still many of the manufacturing companies are doing right now. Okay, so in conventional casting, first we will prepare a pattern. This pattern is nothing but a replica of the casting. So while preparing pattern, we will consider lot many allowances into practice. Okay, so lot many allowances in the sense we will consider the taper allowance, distortion allowance, machining allowance, draft allowance, shrinkage allowance. Likewise, we will consider lot many allowances into practice, and considering all the allowances, we will prepare a bigger size pattern. So that is how we do generally. Okay. Then after once the pattern was prepared, we will take the mold cavity. Then we will pour the molten metal into the mold cavity, and at last we will be getting a final casting. Okay. So once after we have acquired a final casting, do we think that is it possible to use it in as casted condition means? Then definitely no. Actually, this casted component, it needs to undergo lots of post processing. Post processing in the sense either it can undergo some machining process, or else even it can undergo some polishing process, or else even it may undergo some kind of heat treatment processes. So likewise, a lot many post processing will be there. So from here, what we are understanding is in conventional casting routes, the material wastages are very high. Okay. What is the main motto of Industrial 4.0 is to incorporate the digital technologies and also to judicious use of materials in order to minimize the carbon, CO2 footprints in our pristine environment. Okay, actually we are facing a very huge environmental degradation in these past decades. It is because like lot of companies are emitting lot of pollutant, lot of pollutions. So in order to minimize the pollution, and also in order to improve the part accuracy, and in order to improve the degrees of freedom, and in order to utilize the material in a judicious way, this industrial 4.0 is working on. Okay, and why we need to judiciously use the material? Why don't we go for the casting itself? That questions may arise in our mind, right? So, say for an example, we are taking a material like titanium 6Al 4V alloy, okay? So, which is one of the most popular aerospace alloys right now, okay? So, that kind of material is having a very poor thermal conductivity in the range like 9.5 watts per meter Kelvin. So, very poor thermal conductivity. So such kind of materials and all, it is very tough to machine. Okay, so if we are preparing a pattern and if we are removing lot of material, then material wastage is one more. Is one way of incurring lot of cost. Okay, a lot of fabrication cost. But in the other way, we have to think that the increased tooling cost also that will be there. So these together it constitute a very huge amount to the end customers, and it will affect the affordability limit. Okay, because tough to machine materials when we are trying to machine it out, then obviously the tool will undergo wear very quickly, because it has very poor thermal conductivity, and the tool will have some kind of build-up edge, which is like the that material will recast that material that will get deposited in the tool itself, and it will further promote the tool wear. So in order to improve the efficiency of the component manufacturing, right now industrial 4.0 is like emphasizing the modern manufacturing companies to deploy the advanced technologies. Okay, yeah. And whereas in terms of additive manufacturing, okay, additive manufacturing is a layer by layer approach, as I told you earlier. It is like a bottom up approach. In additive manufacturing, initially we will be doing all the path planning and everything. Once it is done, if once we give a command to the robot, then this industrial robot, this welding robot will be like fabricating a component more or less to the exact shape of the component. Then after that, if we necessary, we can do some post processing, or else we can use it in the as printed condition. So it is up to us. Okay, so likewise we can do. So the steps are like very very simple. Okay, not that much time consuming as casting. Okay, actually right now we are facing a huge demand for products where time is very very precious. Okay, so in order to improve the time efficiency, we are going for this kind of like digital technologies. Okay. Let us see what are the allowances we consider in casting. In casting, as I told you earlier, lot many allowances are in practice. But whereas in WAAM is concerned, we will be considering only the shrinkage allowance, machining allowance, and distortion allowance. Only these three are generally considered. Okay, so today we are going to see only about the metal additive manufacturing. So in that, metal additive manufacturing is like broadly diversified into three types. So one is powder bed fusion technologies. The second one is direct energy deposition, and the third one is the binder jetting. Okay, so as today's topic of interest is wire arc additive manufacturing, we will be focused only into direct energy deposition. Okay, so this wire arc additive manufacturing, it falls under the category of direct energy deposition, where some few other technologies are there. The name itself indicates wire arc additive manufacturing. Okay, so an arc welding process is being employed. That is why the name itself it was termed as wire arc additive manufacturing. Okay, but whereas this powder based fusion technologies are concerned, so it generally uses powder as the feedstock material. Okay, feedstock material in the terms generally whichever the component we need to develop, or in what material we are going to develop, so that will be generally called as a feedstock material. That feedstock material should be available in the form of powder. Okay, but whereas in direct energy deposition, we can use wire as a feedstock material, or else powder as the feedstock material. But whereas the wire arc additive manufacturing is concerned, we are going to use only wire as the feedstock material. Okay, and let's see what are the basic differences between this powder based additive manufacturing technique and also wire arc additive manufacturing technique. Okay, so let me start with this powder based additive manufacturing technique. Okay, so one of the most commonly used this powder based additive manufacturing technique is a selective laser melting technique. Okay, so selective laser melting means the name itself indicates that a laser is used as a power source here. As we can see now, just a second. As we can see, the laser is like focused into the specific area of the powder, and wherever the zones are exposed to the powders, those areas are selectively melted and the remaining zones are staying unaffected. Okay, so even for fabricating a smaller component, we may need to stack this much volume of powders. And one more thing with the laser powder bed fusion technologies is the initial setup itself, it is very costly, and also the powder cost is very high. For an example, if you want to fabricate a component, the first question is what should be the powder diameter. So can we use any powder diameter? Definitely no. If we are selecting a powder, it should be in certain aspect ratio like 30 micron, 50 micron, 80 micron. Likewise, some aspect ratio should be maintained, and all the powders should be of spherical morphology so that the laser beam can easily focused in a particular zone, and all the materials will get properly melted, and we will be getting actual component without any geometrical irregularities. Okay, so if the powders are not spherical in shape, if the powder is irregular, then we will face a lot of challenges such as porosities, unmelt fused powders, balling effect. So all these things that comes in laser powder bed fusion technologies. Okay, and whenever we are using a powder as a feedstock material, so we should remember one thing: a lot of porosities also will be there in powder based technologies. But the most advantageous thing with the powder based technologies is this powder based technologies are very highly high precision component can be fabricated. Okay, maybe if we want to fabricate a high precision component and that too a very small component or some limited build size component, we can go for laser powder bed fusion based technologies. Okay, so here we can see as I told you earlier, in laser powder bed fusion technologies only selective areas will be melted and remaining zones that will stay unaffected. Okay, here and all unmelted zones that will stay unaffected. And another most common problem with the laser powder bed fusion technologies is like whenever the material is being melted, so some zones, some partial remelting zones will be there. In those particular zones, that powder won't be fused with the component properly. Okay, so which will be like acting like a burrs. Okay, burrs are nothing like some extra projections in the component, which we generally call it as burrs. Okay, so even if you are doing some some zones where some unfused powders are there, if you want to do sieving and if you want to reuse the powders, then that powders, it won't have a very good quality as the virgin powder. Okay, so this is one of the major drawbacks in laser powder bed fusion technologies. Okay, so in order to overcome such kind of challenges, especially from the cost viewpoint, this additive manufacturing technology has been developed. Okay, so wire arc additive manufacturing technology has been developed. The name itself indicates that wire arc additive. Okay, a wire is used as a feedstock material and arc welding power source is being used. Okay, so this particular technology is more versatile to build even a huge component, unlimited build size, even we can go for that. But even we can build a huge component in a very economical price. Okay, with a very good cost efficiency, we can build it. Okay, so that is a major advantage of this wire arc additive manufacturing technology. As this technology is concerned, generally three main power sources are being used in practice. The first power source is gas metal arc welding process. Okay, so the gas metal arc welding process, this particular technology has been in practice since the 1950s itself. This technology was widely used, especially for welding purpose, for joining similar and dissimilar materials. This technique has been used. So any material that is available in the form of wire, that could be melted using the GMAW power source. Okay, it is shortly called as GMAW. Okay, so here we can notice that wire itself will be acting like an electrode. The wire will be fed in the torch, in the welding torch, and it will be directly melted and it will be deposited over a substrate. Okay, so workpiece in the sense we mean it as a substrate. Okay, over the substrate, this wire will be melted and it will get deposited. Okay, these are most commonly used power source so far. and this particular power source is capable of depositing, okay, aluminum, any grade of aluminum like aluminum 2024, aluminum 2319, even aluminum 4043 alloys. Even it can process inconel alloys, I mean nickel based super alloys, like inconel 718, inconel 625, even duplex stainless steels, stainless steel 316L, okay, even titanium 6Al4V alloy, even such kind of varieties of materials that could be fabricated using the GMAW power source. But when it comes to GMAW power source, there are some discrepancies also as well, okay. So this GMAW power source is concerned, it has very poor arc stability, okay. Generally a conventional GMAW power source, it has poor arc stability, so which will lead to a lot of arc blow in the sense spatter. I will show you in the upcoming slides. We will see more on spatter, how spatter has been formed, how it affects the geometrical fidelity. So those things we will see in the upcoming slides, but generally keep that in your mind. GMAW power source is more suitable for depositing wide range of components, but still the arc stability is relatively poor as compared to plasma arc welding or GTAW welding process, okay. So that is one of the drawbacks, but still this technique is viable to deposit a component in the range of like 2 to 3 kilogram per hour, okay. In 1 hour it can even deposit 3 kilogram of 3 kilogram of material it can melt and deposit, okay. So that is a maximum deposition efficiency which they have achieved so far in GMAW based process. The second process is GTAW process, which is popularly called as gas tungsten arc welding process. So this technique was there since 1925, which is so earlier as compared to GMAW process. So in GTAW process, here we will be using a non-consumable electrode, so which is made of tungsten. Generally, this non-consumable electrode, this tungsten rod, will be used for many applications because it is having a very high refractoriness, and particularly in wire arc additive manufacturing, this particular GTAW tungsten rod, it is like this particular rod, it is generally thoriated tungsten rod. It was the tungsten rod was doped with thorium. It is a radioactive species element. Why it is being doped means so that it can emit lot of free electrons from the electrode, okay. So that is called thermoionic emission, okay. Thermoionic emission means now how much amount of free electrons it can liberate, okay, once we apply a potential difference, okay. So that is what the idea is all about. In any GTAW or plasma arc welding process, we use thoriated tungsten rod, okay, and 2 to 4% of thorium can be added with the tungsten, so that a lot of thermionic emission will be taking place, okay. So for that only we are using GTAW. Okay. And this GTAW is capable of melting wide range of materials. It can deposit a wire of any thickness, like 1.5 mm diameter also it can be melted, even 1 mm diameter, or even it can range up to like 1.8 mm diameter also it can easily melt, because the heat source which comes from the GTAW torch is very high as compared to the GMAW process. So in GTAW process the heat input is quite high, and it can range up to like 10,000 degrees Celsius, okay. So that much high heat input it can provide, okay. But what is the major thing is in GTAW process the wire feeding is the biggest problem, okay. So especially in additive manufacturing is concerned, as the torch is getting rotated, because whatever the geometry is there, the torch also will get rotated accordingly. When the torch is rotated, the wire which is feeded externally, the wire also should get rotated in accordance with the torch, okay. So that needs to be synchronized, so which is one of the existing drawbacks of this technology as compared to GMAW, because in GMAW the torch itself can easily rotate because the wire is directly fed inside the torch. But whereas in GMAW, in GTAW, the wire is fed externally using any external wire feeder mechanism. This wire can be fed either forward or backward or sideward through any automatic feeder mechanism. But when we are printing a complex geometry, this wire also should rotate in accordance with the torch. So achieving that particular geometrical precision is still challenging, okay. And another most drawback with the GTAW torch is this GTAW torch. It can deposit any material when we are doing it in a slow speed. Okay, slow speed the arc will be stable, but whereas when we are going, I mean, when if we want to deposit more amount of materials, if we are applying the torch traveling speed in a very higher, faster rate, then yeah, the arc will become very unstable, and it will lead to a lot of short circuiting errors. Okay, so in order to overcome this particular challenge, an evolutionary version of GTAW torch, which is plasma arc welding process, has been widely used. Okay, plasma arc welding process is a advanced version or evolutionary version of this GTAW power source. Okay, so here what is the advantage? So in GTAW torch, the arc is like a flaring arc. Okay, but whereas flaring means it is like it will be coming this way. But whereas this plasma arc welding is concerned, the arc is a very converged arc. Okay, so it is a GTAW is a slightly diverged arc, but whereas this plasma arc welding is a very narrow arc. Okay, arc will be very narrow. Just like if you want to perform any keyhole welding, we can go for plasma arc welding process. And also for depositing like a more volume of component. For example, I want to deposit like 6 kg per hour or 5 kg per hour. To that much extent I want to deposit, and that too I want to move my torch in a very faster way, then blindly go for plasma arc welding process. Okay, but what is the trade-off is the heat input. Okay, the heat input of the plasma arc welding process is very high. Okay, because the arc is just a very narrow constricted arc. So the heat input will be around like 20,000 to 30,000 degrees Celsius. Okay, so that much very high heat input it can give. But whereas this GTAW and GMAW, it can provide a maximum heat input like up to 8,000 to 10,000 degrees Celsius. But whereas it is like 3 times higher. Okay, plasma arc welding can produce 3 times higher heat input. Okay, so these are the major 3 power sources which has been extensively used in wire arc additive manufacturing process. Okay, so let's see, once we are going to deposit a component, I mean how the wire is going to get melted and how the droplet is getting deposited into an actual component. Okay, so we will see for GTAW and plasma arc welding, both the processes are a little bit similar only. There is no big deviations in this particular technologies, as it is an evolutionary version. Okay, so let's see how the droplet is getting deposited. Okay, so in figure number A, we can see that if once the arc gets constricted, okay, so there is a gap between the substrate and the tungsten electrode tip. Okay, so there is a gap between that, so that is called as the arc length. Okay, generally in metallurgical terms we call it as arc length. Okay, so always it will be like 1 centimeter. Okay, roughly 1 centimeter, and we will generally keep it as an arc length, standard arc length we will keep it up. And once the arc is getting constricted, we will expose the wire inside that arc, so that this wire will get eventually melted. And once it eventually gets melted, once it reaches a maximum amount of threshold limit, once it has reached, due to like surface tension and also due to the gravitational effect, the molten droplet will get detached and it will get deposited in the substrate. Okay, so this is how the deposition process it goes. Okay, but whereas the GMAW process is concerned, so let us see how the molten pool detachment is taking place. So this particular technology is called as CMT technology, cold metal transfer technology, which is an advanced version of GMAW process. Okay, so conventional GMAW process, it has a lot of it has a lot of problems, such as like spatter, I mean, which I told you earlier, which is nothing like arc blow, where the precision will be very less, and the arc will be very unstable. So the conventional version of GMAW has a lot of problems. So those problems are overcome by the CMT technology. Okay, CMT technology is a modified MIG welding process. Okay, modified GMAW process. So this process can have a very good arc stability. This process is capable of depositing wide range of materials. I mean, wide range electrically conductive materials, and it can deposit a material of even bimetals or even any compositionally graded materials. It is capable of depositing. So it has varieties of applications. Okay. And in this particular technique, how it will be working, let us see. Here you can see the electrode rod, the feedstock material which we are going to deposit, that will be undergoing a forward retract movement, okay, forward retraction movement. So once it is going for a forward retraction movement, the molten droplet gets easily detached and it is getting deposited into the surface. So another most important thing which you should, which we should be noting is, especially, again let me play that video. Okay, again we can see the polarity is also getting altered. Okay, when depositing, the polarity is getting altered. So initially it will be like a straight polarity, like a positive negative, that kind of alternating polarities which we can notice here. Okay, and the molten pool is also very stable. Okay, so that is what we can notice here. So let me explain you what is the polarity is all about. Okay, so generally whenever we are depositing a component, the polarity plays a very crucial role. Okay, in case of like in case of straight polarity. Okay, straight polarity in the sense, so generally the electrode will be connected with the negative terminal and the substrate will be connected with the positive terminal. When we are going to lay a first layer, wherever it is connected with the negative terminal, the avalanche free flow of electrons will be taking place. So the electrode will try to will try to emit lot of free electrons, and that free electrons are carried from the argon gas. Okay, here generally we are using argon as the shielding gas. So the argon gas will get polarized and it is getting charged, and that charged gases will be like hitting the workpiece. So suddenly the arc constriction will be taking place, since the workpiece is like positively charged, and the material deposition will be taking place. Okay, so this is called like straight polarity. Straight polarity, generally the material deposition will be taking place. But whereas in the reverse polarity, why it is being used means, the electrode will be connected with the positive terminal and the workpiece will be connected with the negative terminal. Okay, so in such circumstances, more amount of free electrons will be liberated from the substrate. Okay, why it is being liberated from the substrate? What is the main use of that? Okay, generally, when we are depositing in an open environment. Okay, so when we are depositing in an open environment, a lot of atmospheric gases may interact with our component, and those atmospheric gases that will tend to form a thin passive film in the sense a thin oxide film it will form over the top surface, and eventually that oxides inclusions that will generally go into the material when it reaches a molten form, and which may cause a lot of deleterious effect. Okay, so in order to remove the oxide layers, either we can remove it by means of wire brush, we can remove, but that will cause lot of delamination in the sense surface deterioration. The surface will become more rough if we are removing it with wire brush. But whereas if you want to remove it in an atomic level, then it is generally preferable to go for a pulsing. Okay, pulsing means a consistent changing of polarity, positive to negative, negative to positive. Even for every microseconds, this polarity will be getting altered. Okay, so that is what we generally mean it as pulsing. Okay, so in one half of the cycle, the material deposition will be taking place, and in another half of that cycle, the material oxide layer removal will be taking place. So that is what we call it as pulsing. Okay, so generally when the electrode is connected with the negative, the material deposition will be taking place. When the electrode is connected with positive terminal, wherever the negative terminal is connected, the avalanche free flow of electron will be there from the workpiece side. So it will try to break all the oxide layers in a just like a hammering effect it will do, and it will try to break all the oxide layers in an atomic level so that no surface delamination will be there. Okay, so that is what the pulsing technique is all about, which is very popular in wire arc additive manufacturing. So one thing I would like to note here is, in powder based additive manufacturing, if any oxide layers are being formed, of course it is like it is done in a controlled environment, I agree with that. But in case if any oxide inclusions are getting formed, especially in the time of fabrication, then it cannot be removed. Okay, but whereas in wire arc additive manufacturing technique, though we can do it in an open environment, it is possible to remove all the oxide layers through pulsing technique. So this is one of the advantageous features. And the other most important thing which we should note down is this powder based technologies that requires a specific environment. Okay, environment in the sense like it should be like completely done in a sealed environment where the oxygen will be kept like less than 10 ppm parts per million. So to that extent we have to maintain, and in case of electron beam based deposition, we have to maintain a vacuum, so which is very costly if you are maintaining a vacuum chamber. Okay, and we have to purge the entire system with argon in case of a lot of laser based additive manufacturing technique, I mean powder based additive. So that will increase a lot of manufacturing cost. So those kind of cost and all, it can be overcome by wire arc additive manufacturing, because most of the wire arc additive manufactured components that could be manufactured in an open environment. Okay, because we are providing argon as a shielding gas, argon or helium or varieties of shielding gases can be used. So we no need to provide a closed environment for this. Okay, only for certain materials which are very sensitive to oxide oxide formation. Only for those materials we may need to fabricate a closed chamber. I mean closed glove box kind of environment. I will cover it in the upcoming slides. Okay, so as I mentioned earlier, if we are not concerned about the geometrical accuracy, I mean the surface roughness is not a big constraint, then blindly we can go for this wire arc additive manufacturing process. Okay, because the surface roughness of those components will be ranging from like 45 micrometer to 100 micrometer, to that much high surface roughness it can go up to. So if surface roughness is not a big constraint, then we can go for it. Okay, but whereas if we are like so concerned about like surface roughness and geometrical accuracy, then it is suggested to go for powder based DED. But what is the problem is the limited build size. We cannot build an unlimited build size component using this powder DED process. But whereas in wire DED is concerned, we can build an unlimited component, unlimited build size. We can easy to build. Okay, so yes. So let's see some couple of potential applications of WAAM. Why this technology is increasingly gaining attention. Let us see. So it has been like extensively used nowadays for engine casing fabrication, and for fabricating some ship propeller blades we can use, and even for if any blades are broken. Okay, so generally the defective component will be thrown away and you will buy a new one. Okay, but whereas this WAAM technology is concerned, it can able to reconstruct the damaged part exactly to the desired geometry. Okay, so you no need to throw the old component. Okay, it is possible to rework the component, which is one of the most advantageous thing. Okay, and another is the seawater pipelines. Okay, so generally for like seawater oil pipelines are concerned, we can even fabricate to any dimension and we can fabricate it. Okay, so that is one of the major advantages of this WAAM technology. Okay, so it has potential applications. And the next thing is concerned it has even leaped into some civil structures also as well. Okay, we can see some civil structures in Germany which has been built by this WAAM technology. Okay, so it is in Amsterdam. So it has been this complete civil structure has been fabricated using this WAAM. And also we can fabricate some lattice structures. Okay, lattice structures for aerospace applications we can use. And for energy harvesting application, we can fabricate some lattice structures. Even that could be done by means of this wire arc additive manufacturing technology. Okay, so on seeing all these advantages, it has attracted a lot of industrial players and also academia to work in this particular domain. Okay, so let's quickly step into what are the hardware components of this WAAM system. Okay, so as the WAAM hardware is concerned, we can see generally two hardware systems. Okay, so the welding power source is generally interfaced with two hardware systems. So one is like CNC, computer numerical controllers, we can interface the torch with, or else we can go for this kind of robotic controllers. Okay, these two are extensively used. Okay, so why we have to go for this kind of CNC based CNC based position? For an example, if we are like so concerned about position and precision, okay, so the torch, it should move in exactly this x coordinate, y, this particular y coordinate, this particular z coordinate. That precision and positioning is very good in computer numerical control machining. Okay, it is operated generally like CNC machining is there. So similar to CNC machining, the CNC based microcontrollers are being used, which can where we can control x coordinate, y coordinate, z coordinate in a very precise level. That accuracy will be like will be around like 0.5 mm to 2 mm accuracy we can maintain. And in case of robotics, that precision accuracy is not that good, but CNC has some unique advantages like this. But whereas this robotic controllers can rotate to all degrees of freedom, but whereas it is not possible with CNC controller. CNC controller cannot rotate to all degrees of freedom. That is the biggest problem. And especially when we talk about GTAW process or plasma arc welding process, this CNC based controller is not that suitable, okay, because the wires will be fed like coaxially using any automatic wire feeder mechanism, where the torch and wire both have to melt, both has to tilt simultaneously for making any deposition, okay. So such kind of provisions are not there with CNC based controllers. But whereas these robotic controllers are concerned, you can easily rotate in all degrees of freedom, okay. So that is one of the most advantageous part. But whereas the precision and accuracy of this robotic controller is less as compared to CNC, okay. So that's the thing which you are looking from here. And other than that, there is a newly emerged system which is called twin wire arc additive manufacturing, okay. For example, if I want to develop compositionally graded, which Dr. Professor Lakshmi Narayanan has conveyed in his lecture, okay. Like if you want to build any kind of compositionally graded materials, so for that also it is possible to do it in using this wire arc additive manufacturing. For example, I want to build a component of copper and Inconel 625, okay. If I want to build a component, say for an example, okay, if I want to build it in a functionally graded way, then I can use the CMT power source. I mean, two CMT power sources I can use, and which can be fed to your torch. And if I want to deposit like a 75% of Inconel 625 and 25% of copper, what I can do is I can simply change the wire feed rate, okay. Now if I want to deposit more Inconel, means I will be increasing the Inconel wire feed rate to a greater extent, and I will reduce the wire feed rate of copper, so that I can have more deposition of Inconel and less deposition of copper wire, okay. Likewise, we can alter the wire feed rate of the welding process, and we can build a compositionally graded components, okay. So that is one of the advantageous thing with this WAAM technology, okay. So and added to that, if you want to have a more deposition efficiency, we want to quickly deposit like 10 kg per hour, we want to deposit. For that also it is possible using this twin wire arc additive manufacturing, because like two wires, if both are getting deposited at the same time, then more volume of material will get deposited, okay. Yeah. So other than that, we can install like some kind of features like high speed camera to see the molten pool detachment, how the molten pool is getting detached from the wire. Is there any arc blow is there or not? So all these things that can be captured by high speed camera, and even we can incorporate lot of sensor technologies also as well. So in order to like assure the precision and positioning of this WAAM component, okay. So this is one of the emerging technologies right now, okay. And in order to provide a greater flexibility and greater degrees of freedom, robot torch itself can easily rotate in all the axes, but in order to provide even more versatility to the existing deposition method, we can go for like a rotating jigs and fixtures arrangement we can go for, so that not only the torch will be rotating, the workbench is also will be rotating to any axis, so that we can have very good geometrical accuracy, okay. So we will be having unlimited degrees of freedom we can achieve, okay. So this is also one of the main hardwares of this WAAM technology. And as I told you earlier, if we are fabricating material which are very sensitive to oxygen, okay. Now, as I told you earlier, some few materials like titanium, magnesium, or some materials like aluminium, those are like very sensitive to oxygen. Okay, so it has very high affinity with oxygen, which can easily form any oxides. Okay, like Al2O3 or TaO2, it can form easily oxides. So in order to minimize those kind of oxide formation, we will be going for a completely closed chamber based fabrication. Okay, where the robotic arm will be like rotating inside, and yeah, this complete environment will be filled with argon gas, and the material will be deposited. Okay, so this is how it works. It is particularly for very sensitive materials, not for all. Okay, like regularly we can build any material in an open environment. Only for sensitive materials we can go for this kind of closed chamber environment, which we generally call it as glove box environment. Okay, so we can see some gloves here. So just like only gloves can enter, because completely the system is sealed with argon gas. Okay, so that is how this works. And if any weld fumes are there, that will be like exhausted from a chamber here. Okay, so automatically it will get exhausted. Okay, so no weld fumes will be stagnated, and argon purity will be remaining as it is. Okay, yeah. And other than that, we can use a 3D white light scanner. Okay, which is one of the most vital equipments. For example, reverse engineering is the latest approach, which many people are working on nowadays. For example, some complex geometry is there, which we cannot prepare a blueprint of this component, which is very tough to prepare 3D topology. Then for such cases, we can go for like 3D white light scanners, which can scan the accurate geometry of the component, and it will provide us the exact 3D geometry. Okay, so we no need to draw the component dimension manually. Okay, it is not at all required. The machine itself will take some random images in all the directions, and it will be reconstructing the data, and it will form exact topology of the component. Okay, so that exact topology will be converted into .stl file, and it will be given as an input to the robot. So robot can as it is, it can fabricate within some few hours. It can fabricate a complete component. Okay, so the time which is required for making a CAD geometry or geometrical modeling can be greatly minimized if we are using this kind of 3D white light scanners. Okay, so this is also a part of WAAM technology nowadays. Okay, yeah. Other than that, like in WAAM, what kind of softwares I can use, how I can digitalize. Okay, as we are talking about digital technologies, so this kind of questions will be striking in our mind. Okay, so we can go for general CAD modeling techniques like SolidWorks, CATIA, or anything to construct a geometry. If we don't have that white light 3D scanner, if we don't have, we can use this kind of CAD modeling tools to generate a geometry. And if once we prepare a STL file, that will be given as an input. Input to the robot we will be giving. So based on which the robot will be like fabricating the component, or the CNC will be fabricating the component based on the geometrical codes. Okay, so of course it will be doing. But if it is doing as it is, then it will lead to a lot of errors. It is because the geometry will be very complex, means the machine cannot understand that exactly like in which trajectory it is supposed to move. So it will leave a lot of trajectory errors. So in order to overcome such kind of errors, we will do a process called slicing. Okay, slicing means a very big geometry will be there. That geometry will be sliced into some finer segments, so that the machine can easily understand that in which trajectory it is supposed to move. Okay, so that is called 3D slicing. For slicing, we generally use these two softwares which are widely used for exclusive for WAAM technologies. And and this bead modeling is concerned, as we know, first of all, prior to any deposition, we will do some pilot studies. So this kind of pilot studies we generally do with some bead modeling studies, bead on plate trials, which I will be showing in the upcoming slides. So that we will do it by means of some statistical models we will generally do. And also we will generate tool path planning, means the torch path planning strategies, what direction it is supposed to rotate. Either we can fabricate in a uni layer or like a raster pattern that I will be covering in the upcoming slide. So those things and all that can be properly planned by means of MATLAB. Also we can plan, even Python also we can plan, and also even Abacus also we can plan. And also there is one more software like sysweld software, which is also most versatile software widely used, and even recently Simulia, so that software is also extensively used. Okay, such kind of like software we can simulate, and once we found that okay it is working fine, then we can fabricate the actual component. Okay, so that is how it works. As I told you earlier, the first thing is the bead on plate trial. Okay, so bead on plate trial means initially we want to standardize the width of the bead, length of the bead, and the thickness, the height, and each and everything we would like to get standardized. Okay, how we can do? We can do it by means of some pilot studies. Pilot studies means we will perform bead on trial. So initially we will be performing one bead and we will measure like how the bead profile it looks, how far the bead is stable, and we will see what is the thickness of the bead, height of the bead, width of the bead, everything we will see, and based on the desired need we will standardize that this particular process parameter is the best one. Likewise we will first standardize like what is the what process parameter gives the accurate desired bead that we exactly want. Okay, first we need to standardize that. So once I have standardized the bead thickness, bead height, and everything, this process parameter is the best. Then what I will do, then I will see the macrography. Okay, macrography means initially I will be doing the bead on trial, and I will see the macrography how much the dilution has been taken place. Okay, so this dilution is a common welding term. Okay, dilution means how much is the volume of material that is infiltrated with the substrate. Okay, so that is what we mean it as a dilution here in additive manufacturing term. Okay, so if we are having like lot of dilutions we can observe, so why we need to give this as a paramount importance? Okay, so that question generally arises in our mind. So generally as the first layer is concerned, we have to it has to anchor properly with the substrate. Okay, so the first layer it will properly anchor with the substrate so that we can lay the subsequent layers. Okay, for example, if the dilution is very poor, okay, it is not properly diluted. Diluted means how much it is infiltrated. Okay, infiltrated with the substrate. Infiltration means that will clamp the substrate and it will tend to adhere in a very with very good force it will get adhered, and it will never let the subsequent layers to get peeled out. Okay, so that is why this dilution is very important factor in additive manufacturing. Okay, so we will first lay the layer and we will check the dilution. If the generally for first layer the dilution should be good, the dilution should be high. High means here you can see the dilution is very high. As compared to this dilution is very less, but the bead thickness is high. But whereas this one dilution is somehow less, but as compared to this one is somehow less, this one is also less, and the another one is also less. So based on different bead on trials, we will first standardize the dilution. So the dilution should be very good for the first layer. So we have to deposit with a very high current for establishing a very good dilution. So once I have got a very good dilution, then the next subsequent layers I can lay even with less dilution, that is not a problem. But first layer should have a very good dilution so that it can anchor with the substrate. Okay. And once I have standardized the dilution and all other things, then I will be doing a 3D slicing. 3D slicing, as I told you earlier, a complex geometry will be like sliced into a finer segments so that the machine can easily understand. Okay, so some softwares I have told you earlier, so those softwares, using those softwares we can slice a 3D geometry into finer segments. Then after that we will be planning the tooth path planning. Okay, tool means I mean the torch. Okay, in what direction the welding torch is supposed to move. X-axis how much it has to move, y-axis how much it has to move. So all these things that I will be planning through tool path planning. Okay, I mean torch path planning I will do, so that the torch it won't collide. Okay, the torch won't collide with the workpiece anywhere. Okay, so accordingly I have to plan the torch planning. Okay, because the torch is very costly. If it gets collided with the component, if it hits the component, then the torch may get damaged. So accordingly I have to plan the trajectory. Okay, and in what are the directions it can rotate. Okay, based on the complex geometry I will be planning in which direction the torch is supposed to move. For example, there is a standard pattern which is called as a raster pattern, which has been extensively studied in lot of literatures. Okay, raster pattern means it will be depositing in a unidirectional way. It will be like depositing. And whereas the zigzag pattern is concerned, it will be like once when the torch is moving and when it is retreating back, the deposition will be carried out. Contour means if the component is having a very complex geometry, then we will go for like contour based planning. Then spiral, I mean, if it is a circular component we are going to build, then we can go for a spiral pattern. Likewise, lot many torch path planning strategies are there. So these and all we no need to select. Machine itself will be providing a suggestion that based on our geometry, this path planning will be more appropriate. Likewise, the machine itself will be suggesting, and our job is to like ensure that either that is really working or not. Okay, so we no need to break our head which path planning will be working fine. The machine itself will be suggesting that okay, based on the complex geometry, this particular path planning will be more appropriate. Okay. Yeah. So even few other path planning strategies also there. Hybrid, matte means medial axial transition, adaptive matte. So adaptive medial axial transition. So even this kind of varieties of torch path planning strategies are there. Based on our geometry, we will be deciding it. Okay. So when it comes to WAAM, we will be considering all these factors as a crucial one, because each and every factor that has its own effect. Okay. For example, wire feed rate. Okay. As the wire feed rate is concerned, this wire feed rate, if we are giving more amount of wire feed rate, then more amount of material will get deposited. Okay, so that is one of the things with wire feed, or I mean wire feed speed. Okay, if it is like 3 meter per minute or 5 meter per minute, then more amount of material will get deposited. If it is 1.5 meter per minute, only very less amount of material will get deposited. So wire feed speed is one of the important constraints. Then the shielding gas flow rate. Why it is an important constraint? It is because most of the most of the cases, atmospheric gases may interact with the molten metal, okay, which will result in decolorization. Decolorization means your metal will get decolorized, brown color or black color, it will get decolorized. So in order to prove why the decolorization happen means because your molten pool, it interacts with the environment, so due to which the oxides were being formed, so due to which the metal is getting decolorized. Okay, so such kind of things can be prevented by shielding gas flow rate. Okay, if you are giving a shielding gas flow rate of 20 liters per second, okay, sorry, 20 liters per minute, so that very high shielding flow rate, no oxide can easily infiltrate. If you are giving 10 liters per minute, okay, then obviously it will result in lot of oxide formation. Okay, so the shielding gas flow rate is also one of the important constraints we need to consider. Okay, this torch angle. Okay, torch angle means the torch can be rotated to any angles. Okay, so what angle we are going to rotate? Okay, so as I told you earlier, this GTAW plasma welding process, it greatly relies on torch angle. Okay, so in what angle this torch is going to get rotated, that will be determining your deposition efficiency, and also like how much heat input is going to get delivered. And also it will be determining that either it can fabricate any kind of like complex intricate shapes or not. Okay, because for example curved edges or some kind of like crisscrossings are there. So if we need to rotate, then the torch angle is one of the important constraints. Okay, that which we need to consider. Then the arc oscillation frequency, which we generally call it as weaving effect. Okay, weaving. Okay, weaving is a general term which we generally use, which is otherwise called as arc oscillation. Arc oscillation means the torch will be oscillated like this, just like zigzag, or else it will be like rotating. Likewise, the torch will be oscillating. So that also one of the important factors which we will discuss tomorrow. Okay, I mean not tomorrow. I mean our next session we'll be discussing about that. And arc initiation voltage, how much voltage we are going to give, how much current we are going to give, that will determine your heat input. This pulse frequency. Okay, pulse frequency I told you earlier. How much metal is going to get deposited and how much is going to be your oxide layer removal, that is called as pulse frequency. So we can channelize the pulse frequency. If we want to deposit more amount of metal and less oxide layer removal, likewise also we can channelize the pulse frequency. Pulse frequency is nothing like in one microsecond how many times the positive negative that pulsing need to be done. Okay, so that is what we mean as pulse frequency. Okay, so generally we this pulse frequency we have to plan according to the based on the material. Okay, if it is titanium, more amount of oxide layer should be removal should take place, and less amount of metal can be deposited because titanium can easily get oxidized. Okay, for such kind of thing we have to alter the polarity frequently, but for normal material like stainless steel or inconel, we no need to alter the pulse frequency to a greater extent. Okay. Then robotic path planning. This robotic path planning, it is also one of the important constraints. So in what trajectory the torch is supposed to move, which I discussed with you earlier. and interpass layer temperature, which is a very interesting phenomenon, which I will cover it in the upcoming slide. Interpass layer temperature means the temperature for each and every successive layer deposition. For example, I deposited a first layer. So once I deposited the first layer, this first layer will be of a certain temperature like 1000 or 800 degrees Celsius. When the material is in red hot condition, if I am depositing a next layer, then it will lead to a lot of dilution. Okay, dilution I have shown you previously. Dilution means how much one layer get infiltrated into the another layer. So that is called it as dilution. If more amount of dilution is taking place, then your more volume of material we need to deposit. So it is a material wastage. Okay, so in order to prevent that, we will maintain a interpass layer temperature. First layer I have laid. I will be waiting until the deposited layer will get solidified and it reaches an ambient temperature like 300 degrees Celsius or 250 degrees Celsius. Until then I will wait. And after once it had reached the desired temperature, then only I will lay the subsequent layer. Again, I will be waiting until the previously deposited layer reaches the same interpass layer temperature, and then I will lay the next layer. Likewise, if I am maintaining such kind of interpass temperature, the grain homogeneity also can be achieved, and also we can avoid plate distortion and all other geometrical irregularities. Okay, so interpass layer temperature is also one of the crucial factors. And what is I mean, other than that, I mean, we will perform the interpass rolling and heat treatment and machining techniques are also there, so which we will be covering in the upcoming sessions. Okay, so by now we will give a short break, and after that we shall continue from here. Okay, yeah. Yeah. Yes, sir. Fine. Yeah, yeah. Fine, fine, fine. Yeah, sure. Yeah, sure. Yeah, sure, sir. Yeah, yeah. Fine. Thank you. Yeah. Yeah, I'm back. Yeah. Okay. Okay, from here I think we are stopped, right? Yeah, okay. So let's start from here. So, okay, fine, sorry. Yeah, sure. Is it right now okay? Is it my screen is visible? Yeah, sure. Yeah, fine. Yeah, thank you. Um, actually, this wire arc additive manufacturing is concerned. Okay, so we will be using like varieties of shielding gases. Okay, as I told you earlier, this wire arc additive manufacturing, it doesn't need a controlled environment. So even we can fabricate in an open atmosphere also as well, because we are using a shielding gas. Okay, so there comes a question like what type of shielding gases we can employ. Okay, so generally we can go for pure helium, or else we can go for argon, or else in case if we want to fabricate some special materials like inconel 718 or inconel 625, then we can go for a metal active gases also as well, like argon plus hydrogen. Okay, argon is a metal inert gas, hydrogen is a metal active gas. Okay, so mixture of both we generally call it as metal active gas welding. Okay, so that kind of metal active gas also that could be employed for depositing wide range of materials. And also we can use like argon nitrogen and also argon CO2, I mean carbon dioxide also, it was generally used. Let us see why. In welding, generally helium is being used. Why helium is being used means wherever we want to achieve a greater depth of penetration, especially in the welded joint, then we generally go for helium gas. Why means why helium has that tendency, if you ask me, because helium has very high ionization potential as compared to argon. Okay, so just for the same power, same voltage, if a GTAW torch is producing an arc, okay, for argon gas, just imagine that temperature is like 10,000 degrees Celsius. Okay, but whereas for the same voltage, same current, if we are using helium as a shielding gas, then the arc temperature will be very high. It will be like 13,000 or 15,000. To that much high extent, the arc temperature will get increased. It is because helium has higher ionization potential as compared to argon. Okay. So what is ionization potential? Ionization potential means how easily the gas can get polarized. Okay. How easily the gas can get charged. Okay. If the ionization potential keeps on increasing, then the arc which is extinguished by the process, that will be like keep on increasing. The temperature, arc temperature will be very high. Okay. For an example, argon hydrogen mixture. Okay, argon may have a ionization potential like 13.4 electron volt. Hydrogen may have a higher ionization potential like 15 electron volt. So when we mix these two different shielding gases, then the arc temperature also will be very high. Okay, argon plus hydrogen shielding gases will provide a very high amount of arc energy. Okay, but whereas argon and nitrogen both have almost a similar ionization potential. Okay, like argon may be 13.4 electron volt, means argon, I mean this nitrogen may have 13.6 electron volt. There is no big difference. Okay, so in such circumstances the arc temperature won't be that much high. Okay, argon CO2, in argon CO2 almost CO2 also having more or less similar to the ionization potential of argon, so there won't be that much greater difference. Okay, so in welding this is how it has been extensively used. So why particularly hydrogen will be used for inconel 718 and inconel 625? So we know that there is in inconel 718 and inconel 625 there is a detrimental Lavis phase formation is one of the biggest problem. Okay, that I will show you in the upcoming slide. So in order to minimize the detrimental Lavis phase, we generally go for hydrogen. Okay, argon hydrogen mixture we generally go for that. Okay. So that hydrogen can have a greater ability to minimize the Lavis phase. I mean, this is a detrimental intermetallic formation. Exactly at the grain boundaries it will tend to form. So that detrimental intermetallic can easily initiate cracks. Okay, and it is not suitable for fatigue or tensile applications. So in order to overcome that, we generally go for argon hydrogen mixture. So why we generally go for argon nitrogen mixture means, for example, we are going to deposit a stainless steel, okay, any grade of stainless steel 316L. Then it is a dual phase stainless steel where austenite is a major phase and ferrite is a minimal phase. Austenite will be of more than 95% and ferrite will be less than 5%. So that is the phase composition. So as we know, this nitrogen is one of the strong austenite stabilizers. Okay, austenite is a highly unstable phase, especially during the time of solidification. Some retained ferrite may come. Okay, so in order to make more volume fraction of austenite, we will add nitrogen mixture. This nitrogen will stabilize the austenite phase so that more amount of austenite will be there, less amount of ferrite will be there. Why? If the ferrite is increased, then what will be the problem? Okay, you may be asking me a next question. So if the ferrite is very high, then the corrosion resistance will become very less, as the austenite has very higher resistance to corrosion as compared to ferrite. Okay, ferrite can provide good strength to the material, but austenite can give more ductility and also it can enhance the corrosion resistance. Okay, so from that perspective, we need more fraction of austenite and less fraction of ferrite. So in order to increase the austenite fraction, we generally go for nitrogen. We generally add nitrogen with the argon. Okay, and added to that, this nitrogen can give more than like 10 times better corrosion resistance than chromium, and it will act as a better austenite stabilizer. Okay, so for that application, this argon nitrogen gas is being used. And argon CO2 gas, why we are particularly using it? Okay, for example, I am going to fabricate a material like P91 stainless steel. Okay, take an example. Okay, P91 is one of the boiler grade stainless steel. Okay, boiler grade means, as we know, that high temperature creep is the most concerned requirement. Okay, high temperature creep. As we know that if we are having a coarser grain structure, that is very beneficial for high temperature creep application. For finer grains are not generally preferred for high temperature creep. Okay. So if we want to withstand that high temperature application, then the grain boundary should be very stable. Okay. So in order to stabilize the grain boundary, some kind of carbides, if that is getting formed exactly at the grain boundary, then it can pin the grain boundary and it can offer a better stability to the grain boundary even above the equi-cohesive temperature. Okay, that equi-cohesive temperature generally we call it as like the temperature at which the strength of the grains and the grain boundaries are same. Okay, so that is what we call it as equi-cohesive temperature. So above a particular temperature, the grain boundary may lose the stability. So at that time, we need more stability to the grain boundary. Some carbides, if it is there, it is more beneficial. Chromium carbide or niobium carbide or molybdenum carbide, those will give very high stability to the grain boundary. For that, argon plus CO2 gas is being used, because the CO2, the presence of carbon, that will get diffused inside the molten metal, especially during deposition. So that diffused carbon will provide a lot of strength, high temperature creep resistance to the material, especially material like stainless steel 347 or P91 grade stainless steel. It is extensively used. Argon plus 20% CO2 mixture they will use. Okay, 10% to 20% CO2 they will use. Okay, so this is the application. Why this particular shielding gas are being used right now, we are clear. Okay. Generally, in wire arc additive manufacturing, we fabricate single wall and multi wall components. Okay, so initially we will conduct a feasibility study how a single wall component will be looking and how a multi wall component will be looking. Okay, so initially the single wall components are concerned, we will be like fabricating in a very thin layer. Okay, and this whatever may be the component geometry, it can easily get fabricated. Okay, for example, if I want to produce a pressure vessel, okay, so the pressure vessel will have a very thin bead geometry. So such kind of thin bead geometry, we generally mean it as like single wall deposition. If two or more beads are getting involved parallelly, then we call it as like a multi wall deposition. Okay, multi wall deposition, which is shown here. Okay, just a second, let me turn on the pointer. Okay. So here we can see the multi-walled deposition. Okay, so in multi-walled deposition, we can see like more amount of beads were parallelly deposited, and we have got a very good geometry here. Okay, so this is like a titanium material. Okay. So I was previously talking about decolorization of the material. Okay, if we do in open atmosphere, what may happen? Okay, so the metal will tend to decolorize. Here we can see the titanium have got decolorized into some bluish green color. So this decolorization is mainly due to we have fabricated in an open atmosphere. So due to which the atmospheric oxygens are getting attracted, and the metal has become decolorized. Okay, so if you do it in a closed chamber, this kind of decolorization issues can be avoided. Okay. Yeah. So generally we fabricate, if once we have standardized the bead on trials and we have standardized the bead size, bead width, everything once we have standardized, then we will tend to do some pilot experiments, like how far the bead will be working, either will it come consistently if we are depositing a component or not. So to do that, we will conduct a feasible study like single wall deposition, multi wall deposition, how the bead is coming. Likewise, we will do the pilot experiment. So once after we have done this, then we will examine the microstructures and also the crystallographic orientation. Okay, so that is how the research flow that goes. Okay, so generally, what type of microstructures we can expect in WAAM? Okay, so in WAAM, actually, one thing I am supposed to clarify. The main difference between a casting and this welding is like in casting, the heat will be a static heat. Static heat means the heat will be stagnated in one particular zone. Okay, only in a one particular zone the heat will be like stagnated. The heat is not. A regular heat flow will be taking place, and the heat will be a very static heat. It is not a moving heat. But whereas as wire arc additive manufacturing is concerned, it is a transient heat. Transient heat means it's a moving heat. As the torch it moves, the heat dissipation also it will be varying. Okay, so planning so how the heat dissipation is, that is quite very complex. Okay, now especially in multi-wall components, it is even more complex. Like we can't even predict how the heat dissipation it is taking place. But whereas in casting, we know that how the heat dissipation is taking place. Heat dissipation will take place only through the side walls generally, because if once we are pouring a molten metal into the mold, then the side wall will be acting like a heat dissipation agent, and it can quickly extract the heat from the side wall. So the heat dissipation will be more faster. Okay, so that is how the heat dissipation will take place in casting. But whereas in additive manufacturing, it is not possible to easily predict how the heat dissipation will take place. Okay, so since it is a transient heat source. Okay, as wire arc additive manufacturing is concerned, the solidification rates are very less. Okay, like the metal will take more time to get solidified. Okay, so due to which we can expect only like columnar grains, or very rarely we can expect some kind of EQXZ grain. So how we will tell that only columnar dendrites may get formed or EQXZ may get formed? So in order to substantiate our grain formation, we generally go for this G by R mapping. Okay, G means thermal gradient, and R is the solidification rate. Rate means we can say it like the grain growth velocity. Also, we can say it as it is a solidification rate. Okay, so how fast a metal can solidify, based on which this microstructural evolution can happen. Okay. So, if this powder-based additive manufacturing is concerned, the solidification rates are very, very high, like 10 power 5 Kelvin per second or 10 power 8 Kelvin per second. So, that much very high solidification rates can happen in powder-based, like selective laser melting or direct metal laser sintering. The solidification rates are very high, okay, 10 power 5 to 10 power 7 Kelvin per second. But whereas wire arc additive manufacturing is concerned, the solidification rates are relatively poor, hardly 280 Kelvin per second or 290 Kelvin per second. That itself, I mean, very, very complex. Okay, so achieving that itself a very high tedious task, especially in wire arc additive manufacturing. So the thermal gradient will be very, very high. Okay, the thermal gradient will be very, very high, due to which there are more chances of formation of columnar grains or EQXZ grain. Only these two grains can be more prominent, especially in wire arc additive manufacturing. Okay, but whereas in powder-based additive manufacturing, cellular grains may get formed, or cellular dendrite may get formed, or some EQXZ grain may get formed. But whereas in wire arc additive manufacturing, it is like it is very, very rare to see any cellular grains. So due to very high thermal gradient. Okay. As we deposit a subsequent layer, more amount of thermal gradient will be stagnated. So due to which, due to the complex thermal history, we can expect only columnar dendrite or EQXZ grain morphology. Okay, so that is what we are making our point clear. So in WAAM, we know that only the solidification rate that changes based on the torch traveling speed. Okay, the thermal gradient we can leave it. But once the solidification rate, that is greatly depending on the torch traveling speed, how fast the torch is going to travel. Okay, so generally in welding, we calculate the R, okay, this solidification rate, it is like equal to the torch traveling speed. For example, my torch traveling speed is 20 centimeter per second. Then I will calculate my, I will keep my R as 20 centimeter per second. So that is the solidification rate, because it is a transient heat source. Okay, so once my torch is moving from one end to the other end, the metal is getting solidified. Okay, so that is how we calculate in welding operation. Okay, so these points I made clear. Like most expected grain structure is columnar dendrite and EQXZ structure. Why it is, I have clearly explained. And now let's see some couple of examples. Okay, so in multi-walled stainless steel, how a grain structure will be looking. Okay, so here hereafter we are going to see how the morphology it is going to look, especially in wire arc additive manufacturing. Okay, so in wire arc additive manufacturing, generally we can expect some coarser grains, because the heat dissipation rate is very, very poor, and the heat input is also very high. So due to which this WAAM, we can expect this kind of coarser grain structure only. Okay, but you may ask me a question. Okay, these coarser grains are not that suitable for tensile application or fatigue application. It is not that good. Then how come this WAAM can become a suitable option? Okay, WAAM can become a suitable option for high temperature creep resistance application, because a high temperature creep resistant application, that inbuilt needs a coarser grain. So that as the grains are becoming more and more coarser, then it is more suitable for high temperature application. Whereas for normal application is concerned, wherever we need wherever we need more strength, ductility and micro hardness, for such applications this fine grain is more preferable. But still it is a very challenging task to achieve fine grain structure, especially in WAAM components. Okay, so right now some researches has been carried out in a positive direction, and they have even achieved a very fine grain size. So through opting various strategies in WAAM technology, so which we will discuss in next Friday. We will be discussing about all these things, how we can minimize the grain size. So all these things that will be covered. But generally in as fabricated condition, we can expect a coarser grain in wire arc additive manufacturing. Okay, it is because it will take more time to solidify. As it takes more time to solidify, the secondary dented arms, which we can see here, the secondary dented arm spacing, that will become eventually more. As the secondary dentate arm spacing gets eventually more, a lot of interstitial strengthening elements. Okay, like for example, if you are having niobium as a strengthening element, means the niobium will tend to like segregate. Actually, in stainless steel 316L there won't be any niobium. In case of inconel 625 or 718, I am telling. If we have some niobium, it will tend to segregate, especially at the in between the secondary dentate arms. So likewise, all the strengthening elements will get segregated, and it will deteriorate the complete mechanical properties. Okay. As stainless steel is concerned, some chromium, molybdenum kind of strengthening elements that will tend to preferentially segregate in between the secondary dentate arms, and it will tend to deteriorate the material properties. So how the secondary dentate arms can grow? If the metal takes more time to solidify, then the secondary dentate arm spacing also will gradually get increased as that more temperature is taking to get, as more time is getting to solidify. Okay, the secondary dentate arm gradually increase, which will deteriorate the mechanical property. So this is how the exact structure it looks. Here we can see some gamma sternite and delta ferrite structures which we can see. So and after that, one more example is also there. Titanium 6Al 4V alloy. As I told you, this is one of the common aerospace alloys. Okay, so this titanium 6Al 4V is concerned. The most common expected structure is a basket weave structure, which is a typical morphology for this titanium 6Al 4V alloy. So this kind of titanium, it has a dual phase. One is alpha titanium and beta titanium phases. Especially in WAAM, the alpha titanium phase will be the major phase and beta titanium will be very minimum. Based on the solidification rate only it will be determined. Okay, so how fast the solidification is, based on which the alpha beta phases can vary. If the solidification, especially a material like titanium 6Al 4V, once we fabricate, especially at the molten state, the metal will undergo transformation from, actually TiO6Al 4V is a HCP alloy. That HCP alloy will get converted into BCC phase above like a beta transformation temperature. Okay, because it is alpha beta alloy. So above above certain temperature, like 940 or 970 degrees Celsius, all the alpha phase will get converted into a beta phase, and it will form a grain boundary. And especially upon solidification, again the beta titanium phase will get converted into alpha phase, and it will tend to get solidified, and it is forming a basket weave kind of structure. Okay, so this kind of basket weave structure is a typical morphology of titanium 6Al 4V alloy. So if you ask me a question, either this basket weave structure is more beneficial or not, means pure basket weave structure is not beneficial. Now if it is like a more amount of EQXZ grains, then it is more beneficial. Basket weave is good, but not that good as we expect. Okay, so there are methods to tailor. Instead of getting a basket weave structure, there are methods to tailor in wire arc additive manufacturing to achieve direct EQXZ structure instead of this kind of basket weave morphology. Okay, so this basket weave morphology, it is getting formed because of repeated thermal cycle. Okay, one layer I am depositing, subsequent layer I am depositing, lot of complex thermal gradient is getting built. So due to which I am getting this kind of basket weave structure. Okay, where the alpha titanium is very maximum and beta titanium is very minimum, like less than 5% beta titanium, and greater than alpha titanium will be more than 95%. Okay, so that is how this titanium 6Al 4V microstructure it looks, especially in the WAAM component. As you can see, more amount of like columnar trunk of columnar grains were also formed. It is because this kind of very big grains can form, especially due to the poor solidification rate. As WAAM is concerned, it is known for very poor solidification rate, so the grain tend to grow in opposite direction to the heat flow direction. Okay, opposite direction to the heat flow direction means we know the bottommost region is the easy heat flow direction, because the heat transfer it takes place from the top to the bottom, the heat transfer will take place. So the grains will tend to grow from bottom to the top, opposite to the direction of the heat flow direction, the grains are tending to grow. As a simple example, we can say that opposite to the direction of the sunlight, a plant is growing. Okay, so just very similar to that idea we can see here, like opposite to the direction of the heat flow direction, the grains will tend to grow. Okay, yeah. And if you ask, okay, is it everywhere we will get the same microstructure in WAAM? It is not possible. Okay, obviously WAAM is known for microstructural heterogeneity. Okay, heterogeneity means everywhere different grain size, different grain orientation you can notice. Okay, So in a single wall component, okay, just it is a cross-sectional morphology of a single wall component. The top layer was featured with very coarser grains, middle layer with somehow intermediate grains, bottommost layer with very somehow fine recrystallized grains can be noticed. Why this kind of variations were there? It is because this particular zone, it may have a specific G by R ratio. I mean, like a specific thermal gradient to the growth velocity. The thermal gradient will vary from top layer to the bottommost layer. Okay. Initially, the substrate is there, which is adhered with the component. The substrate will be acting as a better heat sink. Okay. So generally, when we are laying a first layer, second layer, the substrate can quickly evacuate the heat from the component, and it can lead to a finer grain morphology. But whereas as we lay subsequent layers, the base plate, the substrate itself will become overheated and it cannot act as a better heat sink. So the heat stagnation will be generally taking place. So due to which the middle layer may have slightly coarser grain, and in the top layer the heat stagnation will be more even. It cannot quickly dissipate heat because already middle layer also overheated, bottom layer also overheated, the substrate also got overheated. So due to which the top layer will experience a very slow solidification that result in coarser grain formation. Okay, so this is how the grain morphology that varies. So it is not a constant phenomena, it will be changing accordance with the place. So that is called, we call it as like a microstructural heterogeneity. Okay, so this is what will happen with a titanium 6Al4V alloy. Okay, but whereas let us see in Inconel 625 alloy. In Inconel 625 alloy, especially in WAAM fabricated Inconel 625 alloy, the bottommost layer was featured with cellular grain, the middle layer with columnar dendrite, and the topmost layer with like this columnar dendrite with secondary dendrite arms. Okay, so it is also due to the complex thermal history. So we cannot blindly say that a top layer will be having this particular morphology, middle layer will have this particular morphology, and bottommost layer will have this particular morphology. Likewise, it is very hard to predict. It is because it is a transient heat. So the thermal gradient that varies with each and every instantaneous point. Okay, even in the same layer, one point may have a different heat dissipation rate and it may have a different thermal gradient. The another end may have a different thermal gradient. So within one single layer itself, this much microstructural heterogeneity will be there. So we cannot expect a uniform material characteristics in wire arc additive manufacturing process. Not only in wire arc, even powder based also, it is very hard to expect a uniform microstructural homogeneity. So due to which the material will tend to behave anisotropic. Okay, anisotropic means the change in properties with respect to the direction. Okay, so which we are going to cover in the next Friday. Okay, so generally let us remember a term, anisotropy. Okay, yeah. And whereas in multi-wall layer is concerned, I mean multi-wall WAAM fabrication is concerned, so far we have seen only single layer, single wall additive manufacturing. As the multi-wall additive manufacturing is concerned, here also we can see a lot of dilutions here we can notice, and the microstructural heterogeneities were there very maximum. Top layer was coarser, middle layer was even coarser, bottommost layer was having some fine crystallized grains. Why means, so generally after certain amount of heat stagnation, because the bottommost layer will be, because heat dissipation will take from top to bottom, so bottommost layer can quickly dissipate the heat, but once the base plate itself, I mean the substrate itself get overheated, no longer heat dissipation can be possible. So the substrate, overheated substrate and the bottommost layer will have a lot of heat stagnation, which will result in evolution of stress-free grains. We call it as recrystallized grains. So that is how the bottommost layer was featured with some fine grains. Okay, so but whereas the top and middle layers were featured with coarser columnar grains. Okay. And how the microstructure that varies with the layers. Okay, so in order to show that more precisely, we have shown this in the nth layer. Nth layer means it is the first layer. Where it was like in a few other studies have reported that it was having a very coarser grain, and the second layer was featured with say n plus 1 layer means it is the second layer was featured with the less coarser grain, and n plus 3 layer was finer grain, and n plus 5 was like more finer grains. Okay. So this statement is quite contradictory to the previous one. Okay, because in previous we have seen that the top layer was featured with coarser, middle layer was featured with the less coarser, and bottommost layer was featured with very fine grain. But whereas in this case it is like quite contradictory. Top layer was featured with coarser and middle layer with even more coarser. I mean less finer. And n plus 3 it is getting finer, and n plus 5 the top layer is getting even more finer. So how this can happen? Okay, so how this can happen means it is all depending upon the plate thickness. Okay, for example, if you are using a very thick plate, okay, substrate, if you are using a very thick substrate can have a very good heat dissipation rate. But whereas if you use like a 12 thick or 5 thick plate, over that plate if you are depositing subsequent layer, then more amount of heat stagnation will take place in the bottommost layer. Okay, then that will result in lot of complication. Okay, so based on the thickness of the substrate only, the cooling rate will be determined. Okay, as we know that titanium is having very poor solidification rate. Okay, because the thermal conductivity is very poor. Okay, in such kind of materials, we have to go for a very thick plate. Okay, because so that the heat dissipation can be even more faster. Okay, so due to the plate thickness, this kind of microstructural variation can happen. So that is what I am trying to explain here. Okay. And another example, it is one of my unpublished works. Okay, one of my PhD works it is. So in this I have fabricated like a multi-layered, multi-wall stainless steel 316L component. In this, in here also we can see the microstructural variations were there with respect to each and every layer. Okay, the topmost layer was featured with a equiaxial grain. The middlemost layer was featured with columnar dendrites. But whereas the bottommost layer was featured with a mixture of some kind of like columnar and equiaxial morphologies. Okay, so such kind of microstructural variations are more prominent even with stainless steel 316. Okay, so it is not like based on material. With any material, the microstructural heterogeneity is noticed in WAAMs. Okay, so that is what we are clarifying here. So why this microstructural heterogeneity? What it can happen? I mean, what it can trigger? Now, I mean, why it should be considered as a very serious phenomena means, especially we can see from the zone 1, okay, the top layer of the zone 1, we can see the chromium nickel content. I have taken the similar stainless steel 316 as an example. Okay, so in top layer, the nickel chromium ratio we have to see. Okay, so we can see like the ratio is like is almost very minimum. But whereas here the chromium nickel ratio is a little bit high, but whereas in the bottommost layer, the layer 3, the chromium nickel ratio is somehow very less. Okay, so these top layer and bottommost layer have somehow more or less similar chromium to nickel ratio. Why I am talking about this means, this chromium nickel ratio that determines how much ferrite is going to get segregated in a particular zone. Okay, if the chromium nickel content is very less, I mean the chromium nickel ratio is very less, it means that more amount of austenite will be there in that particular area. But whereas if the chromium nickel ratio is very high, say here in the middle layer, the chromium nickel ratio is very high. Okay, so in such areas, ferrite will tend to preferentially segregate. Okay, so ferrite, if it is distributed all over the component, then it is fine. If it is preferentially segregated in one particular zone, means that will cause that will act as a crack nucleation point. As ferrite is a highly brittle phase, so it will that particular zone will be becoming very weak, and it may trigger any cracking complication. Okay, so that is why the elemental composition should be homogeneously distributed. So if it has this kind of like complication, then again we have to do heat treatment to homogenize all the elemental components throughout the component. We have to do heat treatment. That is unwanted work. Okay, so through fabrication itself, we should try to minimize all the microstructural heterogeneities, and also we should homogenize the elemental distribution. Okay, so due to which a lot of researches are going on how to homogenize the precipitate, how to homogenize the grain size. So a lot of work is going on in this particular direction. Okay, yeah. And yeah, we're running out of time. Okay, when concerned about the build orientation in the sense like in what direction the most of the grains are oriented. Okay, for example, if a plant is oriented towards the sunlight, we can say it is perpendicular. But whereas if a grain is oriented, then in what way we can name it out. Okay, so that we can do it by giving some particular texture. Okay, so in this particular texture, this grain is oriented. So which direction the grain is oriented? So that is what the idea of EBSD is all about: electron backscattered diffraction. Okay, so from electron backscattered diffraction, we can able to generate the inverse pole figure through the Kikuchi pattern. Okay, so the inverse pole figure that gives the information that in what direction the grains are oriented. Okay, especially during complex solidification, we are not sure like what direction the grain will orient. Okay, so for titanium 6Al4V alloy is concerned, as above the beta transformation temperature, that is 940 to 970 degrees Celsius, whatever the direction the beta is trying to grow, in that particular direction only the grains will tend to grow. Okay, so this beta titanium is generally a BCC structure and alpha titanium is generally a HCP structure. Okay, so this beta titanium, it will tend to solidify first, and what direction the beta titanium is solidified, in that particular direction only alpha titanium will tend to grow. Okay, so generally as the titanium 6Al4V alloy is concerned, the BCC phase, the BCC structure, the beta titanium phase, that will tend to solidify mostly in 001 orientation. Okay, 001 orientation means which is represented with the red color, red or pink color we can see. So most of the grains that are oriented in 001 orientation, so which is considered to be highly detrimental from the fatigue performance, and also like mechanical properties also it is highly detrimental. But why in this particular direction these grains are oriented? So that will be your next question. Because this 001 orientation is the easy heat flow direction for BCC grains. Okay, for BCC and also for FCC, phase center cubic materials like stainless steel, aluminum. Okay, so for such materials also it will preferentially tend to solidify in 001 orientation. That is the easy heat flow direction. So that is why most of the grains that will tend to grow in 001 orientation, especially BCC and phase center cubic. But whereas in HCP it is different. But whereas for BCC and FCC this is the thing. Okay, so once the BCC phase was got solidified, then what happens? Then automatically the crystallographic orientation was like oriented in 001 texture, which is very detrimental for most of the property, and we can see more coarser grains were there, so which is also very detrimental from the yield strength and for micro hardness perspective. Okay, so this is how the build orientation that looks for titanium 6Al4V alloy. But whereas when comes to duplex stainless steel, it is also similar. Here also you can see some kind of preferential orientation is there, and all the grains are coarser. But somehow here some random grains were there, but mostly we can expect some 001 orientation which is more prominent. Okay, and we can see some couple of examples as nickel titanium shape memory alloy. So here also this 001 orientation is more prominent. Okay, so which is a easy heat flow direction, so due to which more amount of 001 oriented grains are there. Okay, so all these are WAAM components only. So in WAAM components we can expect only coarser columnar grains. Okay, and that too if it is BCC or FCC, we can expect a preferential orientation in 001 texture. Okay, 001 texture we can expect it. Okay, and whereas in inconel soundonite also the similar trend was observed. Okay, here we can see some coarser columnar grains were noticed, and those grains were like grown in this particular most of the grains having this particular texture. Okay, so that we can evidence from here. Okay, and here we can see like I was talking about using of hydrogen gas. Okay, so what is the main use of that? Okay, that we will cover it, that will tend to cover here. As we know, this WAAM is known for poor solidification rate. Okay, so once the solidification rate is very, very poor, so this kind of lavish phase formation will be more. Okay, lavish means it is like a irregular L-shaped phase which is highly detrimental. It consists of a lot of niobium carbide. Okay, a lot of interstitial strengthening elements it contain, so which is like highly detrimental from the fatigue perspective, and also from the tensile strength perspective it is more detrimental. So in order to we cannot avoid this kind of lavish phase, especially in Inconel 65 or soundonite. Maybe we can reduce the size, but we cannot avoid it. Okay, so in order to reduce the size of this lavish phase formation, we may have to go for like faster cooling rate. So if the cooling rate is very fast, this lavish phase, the size of the lavish phase will drastically get reduced. Okay, which you can see here. Wherever the phase got formed, so there and all the strengthening elements have got leached. Okay, so here you can see the leaching of like a strengthening elements in the across the zones, and it is tending to segregate at the grain boundaries. Okay, generally these intermetallics has the tendency to segregate at the grain boundary. So we need to promote the cooling rate. Okay, if we don't promote the cooling rate, it may have this kind of complication. Whereas in stainless steel, sensitization is one of the most common problems. Okay, sensitization means the formation of chromium carbide Cr23C6 or M23C6. Okay, so that is the intermetallic, most common intermetallic, which can get formed in stainless steel 316. Okay, so as the carbon is there, carbon has very high affinity with chromium. It will tend to form chromium carbide at elevated temperature, especially during solidification, slow solidification. Carbon can interact with the chromium and it will tend to form chromium carbide. Okay, as we know that carbon has a very less atomic radii. Okay, carbon has a very small atomic radii which can easily occupy any interstitial voids and spaces. So that is why carbon is an unavoidable species. Okay, even we can call it as a low carbon. I mean the 316L. That L stands for low carbon, but we cannot rule out carbon completely because carbon is very fine atomic radii which can occupy any interstitial voids and spaces. Okay, so that is one of the reasons that carbon can interact with chromium and it can form easily chromium carbide. But niobium carbide is also very high. I mean, niobium is also having very high affinity with carbon. So niobium carbide can get formed very easily. Okay, so which is highly detrimental. So in order to promote that, we have to fasten the solidification rate in WAAM. Okay, so that is one of the critical challenges which which I need to address here. Okay, so these are not okay. Yeah, sure, sir. Yeah, fine. Yeah. No. Yeah. From this, let me end up and I can take questions from now. Yeah. Okay, fine then. Actually, you should remember. Yeah, I understood your question. Okay, so actually, the substrate will be acting like a better heat sink, and you no need to bother about how much it is going to get diluted. But for the first layer, it should have a proper dilution so that the first layer has to properly anchor with the substrate, so that when you lay a subsequent layer, your component won't get peeled out. Okay, so which we generally call it as warping. Okay, warping or that peel out won't generally take place if the dilution rate is very good, especially for the first layer. If the dilution rate is very poor, when you are laying the next subsequent layers, then due to the high residual stresses, the warping will happen from the bottommost layer. Your bottommost layer will get peeled out from the substrate. So that is why we have to go for very high dilution, especially for building a first layer. Then for subsequent layer, you have to minimize the dilution, or else it will consume a lot of material for you. So you have to minimize the dilution for the subsequent layer. But for the first layer, the dilution should be good so that it can properly anchor with the substrate. Understood, no? Yeah. Yeah, but for the first layer, that you can predict. For laying the next layers, you can predict it up. Okay, but for the first layer, you have to concern about the dilution. That is what my point is. Okay, but for second layers and all, you no need to worry about too much dilution. Okay, too much dilution is undesirable for subsequent layers. But for first layer, the dilution is very good. Okay, it should be too much diluted so that it can anchor with the substrate. Okay, so that is what you are understanding. If you want to do some pilot experiments for subsequent layers, you can reduce the dilution by minimizing the heat input. For example, first layer you are laying for like a 110 amperage of current. Then for the second layer you can lay with 90 amperage or 80 amperage. You can reduce the heat input. That is not a problem. But for first layer, you should give with a very high heat input. It should get properly diluted so that it can anchor with the substrate. Yeah. It will generate a distortion means if your plate is sufficiently thick, then why you worry about distortion? So that is what I'm saying. You have to go for a thick plate like 15 mm or 20 mm thick plate. If you are taking, then why you need to worry about the distortion? Definitely it won't get distorted. And maintain interpass layer temperature, so of course it won't get distorted. And if you are depositing continuously, lot of heat stagnation will take place, then it may get distorted. Yeah. Yeah. Okay. Okay, fine. I will actually argon CO2. I never suggested for inconel soundonate. Okay, I was suggested argon CO2 mixture for P91 grade of stainless steel or stainless steel 347, which is a boiler grade. Okay, if you use carbon dioxide CO2 as a shielding gas, then what is? Yes, sorry. Now is it fine? Now is it fine, sir? Now? Yeah. Okay. I mean, I don't know like how to switch off this. Okay, yeah, I'm facing discrepancy. Yeah. So I was saying like argon CO2 mixture is more suitable for P91 stainless steel. Okay, it's boiler grade stainless steel. Only it is more suitable, or a stainless steel 347, which is a boiler grade stainless steel. Argon CO2 mixture is more suitable. Okay, because the carbides are more beneficial. But whereas this kind of inconel soundonate or inconel 65, it is highly detrimental. Okay, so we never generally use for inconel soundonate or inconel 65 CO2 mixture. We never use. We only go for argon hydrogen mixture. Okay, as hydrogen mixture is concerned, this hydrogen, it has a tendency for increasing the thermal gradient, so that the G by, the solidification rate, which will be determined by, the cooling rate E is equal to G into R. Okay, if the thermal gradient G gets increased, then obviously the cooling rate will be faster. Okay, so with that idea only, they have started using argon hydrogen mixture. Okay, so that it can catalyze the solidification rate. And another most problem of using the CO2 is it can lead to arc blow. Okay, the carbon dioxide can lead to lot of spatter if you use argon CO2 mixture. Lot of spatter will be there in your material, because the carbon dioxide will react with a lot of, will be reacting with your molten metal, and it will tend to like blow up, which will result in arc blow or spatter. Okay, so generally CO2 mixture is preferable only for certain materials, but argon hydrogen we can use for a lot of materials nowadays. Yeah. 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 Okay, then go for ultrasonic shot peening. Now, lot many techniques are there. Severe plastic deformation techniques are there. Cold rolling or interpass cold rolling or ultrasonic peening is there. Or else abrasive water jet peening is there. Okay, lot many other post processing techniques are there. Na? Even you can go for hot isostatic pressing. Okay, that pressing can minimize the porosity and it can improve the grain refinement. Even you can try those kind of ways. That would be a better option if your material is non-heat treatable. Anyhow, it is a very good question actually. Yeah, I do agree. But yeah, yes, sir. Yeah, yeah, viable option. Yeah, 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 yeah. Next, yeah, Delhi, sir. Yeah, fine. Okay, so actually, you know, na, every material that has its own unique thermal expansion coefficient. Okay, for example, copper may have a different thermal expansion coefficient. Inconel may have a different thermal expansion coefficient. So when you, it is not possible to weld the material directly. If you weld it, then due to the variation in the thermal expansion coefficient, that the welded zone cracking will be taking place. So that in order to avoid such kind of complication, we are adding the material in a functionally graded way. Functionally graded way means gradually we are adding the doping material, so that this kind of warpage or cracking can be avoided. Okay, so that is what is a method of functionally graded material. For example, a heat exchanger, one end of the heat exchanger should extract heat very quickly, other side the heat dissipation should be slow. So in order to achieve that, one end can be like of material which has very good thermal conductivity, other end can be material which has highly refractoriness kind of material. So when we develop such kind of material in a functionally graded way, we can achieve the desired characteristic. Okay, especially for I have just told the heat exchange application, that is one of the no, one of the applications. Other than that, lot many are there. Yeah, 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 of course. Yeah, thank you. Thank you, sir. Thank you. Yeah, yeah. Yeah, thank you, sir. Thank you. Yeah, thank you. Thank you, sir. Thank you all. Thank you all.